Okay, so now we're going to see how these ideas, how these two operations and three laws are implemented in Lean. But the version we're going to look at is a bit different from the built-in notion of Lean. But there, I mean, just we have a more simpler setup where everything is done in in one structure instead of layering it in more complicated way. Like they do in Lean, but the end result is similar enough that it will not matter for the purposes of this course and will be easier to learn. So, but in Lean and also in our version, we're going to use the term monad for the combination of a bind and a pure operators without the laws, right? So even though mathematically a monad has these laws, we're going to call the version that has the laws a lawful monad. And the reason is, well, when you do programming, you really just care about the operations. You don't have any proving involved. So in Haskell, for example, where monads are omnipresent, well, to be a monad, you only have to have two operations. You cannot even state the properties in the programming language. And Lean is, I mean, follows Haskell in this respect, and therefore we're going to follow our monads, lawful monads. So what do we have? Well, first we have a parameter, which is a type constructor M. So lawful monad is a structure that is parameterized by the type constructor. So in some sense, it's already the first field in some sense of a monad, but it's part of the type. Then you have a has bind. It extends has bind, which provides only one field, which is the bind operation. It has pure, which provides only one field, which is pure. And then it provides three more fields, which are proofs, right? So they're properties, they're lemmas, they're terms of this type, of that type, and of that type. And these are the three laws. Written using the kind of arrow notation, which is a bit more compact than the do's. And these are just the names of the fields. So these, they're basically lemma names. So you have pure bind, bind pure, and bind as such. So we're going to see examples below, so we'll look a bit less abstract. And these two here, these are the Lean versions, right? And when you see that, you think, okay, maybe we'll stick to the version that we've described above, right? So that I've already explained. So right, when we're going to instantiate this type class, we're going to need to specify first, of course, the type constructor, then the two operations, and then prove the three laws. And I should mention, I think this is the first type class we see that actually has some properties here. But you see, because of Curry-Howard, there's nothing to see. There's nothing special. It's just, these are just three more fields with names and types, and the types happen to be propositions, and the values you put in there will happen to be proofs. But there's no fundamental distinction. So we'll cover several instances of monads, several programming idioms that you can achieve, or programming styles that you can achieve using this type class that we've just created. Well, we're basically going to register them so that we get access to this do syntax, and that we can use the monadic laws on also on these new instances that we're going to create. And the first instance is a trivial instance. Always a good idea to start with that. It's the kind of the zero of mathematics, right? At least of additive mathematics. So that's the identity. Identity is just lambda x comma x, right? It's a function that maps x to x, but there's a symbol for it in Lean. It's defined here. And well, pure, moves something into the identity monad. And the identity monad does nothing, right? So this is the same as that. So we can also put the identity function here if you want, right? Identity works both on types and on terms, right? So this identity here takes a type and returns the same type. This one here returns a value of type alpha from a value of type alpha. Because again, Lean doesn't distinguish between terms and types and so on. And bind is also very easy. I mean, all of these IDs here are just for decoration. You have alpha, alpha to beta, beta. So of course, if you have A and F, you just apply F to A. Don't ask any questions, it just works. And then the registration as a lawful monad, right? I mean, here have to pass, this is a bit subtle. I would like to just register ID, but I think, oh, this works. I think this used not to work. It's interesting. I'll make a note of that. Okay. Lean is changing, right? So I developed this material using Lean 3.4, and now we're at Lean 3.22 or something. So, and things have improved, which is great. Okay. So here, we put id.pure. I think we really need the at here, because otherwise it tries to infer an argument, an implicit argument. We don't want it. We just want it to take the function as is and assign it to the corresponding field, which has the exact same signature. So we put an at in front. This is what the at is for. And then we have to prove the three laws. These are very easy proofs, of course. So we have a bunch of for alls here. We do a bunch of intros. But I like to give good names, right? But intros will, well, actually by default here, it also creates pretty good names. But I like to be explicit. Don't want to rely too much on, you know, whatever names Lean thinks are good at that point. But it's a matter of style, so which means we're not going to subtract points because you just use intros without all the names. And then we look at this and like, how are we going to prove that? Well, we can think, okay, well, I'm feeling lucky, right? I mean, there's probably nothing going on here and it's going to be trivial. You just try REFL and it works. Or you say, well, let's try to unfold the definition of that operator. And the trick is to put it in parentheses. And then Lean is happy, and then we see ID bind and ID pure. So we could also unfold that. Right? And then we're done. But you see what everything I've done is unfold definitions, and that's the kind of things REFL can do because it reasons up to definition, up to the delta expansion or conversion rule. And then, well, it's the same thing with pure and ASOC. I'm not going to dwell on that. And yes, so that was the trivial instance, right? So we just put an alpha in a completely trivial box, you know, which is basically no box at all. So you can think of this monad as the emperor's new clothes, if you like, right? The emperor is naked. But we're going to see that the other monad instances are all variations of the emperor is naked, right? It's going to be, oh, the emperor wears a very nice belt or a very nice hat. But now that we've seen the emperor naked, we're going to understand a bit better the other monad instances.